So hello everyone. In this video we'll be discussing, we'll kind of continue from where we have left. So in the last video we have seen different conditions of loading, normal stresses, how it will behave, how the strain energy will look like, in the case of bending how it will look like, and shear and torsion. So we'll be seeing in this video, at least we're going to see these two, normal and bending cases. Try to see both of them together in this. So let's take a case of a normal. So in the case of a normal loading, and let's say it's gradually increasing, normal, or let's say tensile, and it is applied gradually in the sense that is applied slowly and slowly. You are increasing the load. So you have this. What is this? This is a bar. Now you know the difference between bar, beam and column. So, and this is P, and let's cut this beam at any cross section. Sorry, let's say this have a length of L, and let's cut this beam at any cross section. So you'll be having it like this, and there will be, since this is a cut section, so you'll be having a stress resultant. Let's say that resultant will be the same stress resultant we have shown here, sigma. Let's say this is R, and definitely this is a resultant. As a reaction force, this will be equal to P. So what will be the load displacement curve? And I'm assuming here a linear elastic material, and if it is not a linear elastic material, you know how to obtain that. Shown you. So it's a linear elastic material like this. The area under this curve will be the amount of strain energy. So load displacement, and this will be, the area will be U. The area will be U. So in this case, what will be the U? The U will be R times, this is the resultant R that is applying, times delta by 2. Resultant delta by 2. In actual case, that is your R. And what will be your deformation? Deformation delta equals to PL upon AE. PL upon AE. In most of the cases, this is how the deformation is obtained. How this is obtained? How this is obtained? PL upon AE deformation. Let's write sigma equals to E epsilon. Sigma equals to P by A. Sigma is usually equals to E epsilon by Hooke's law, and it's also equals to P by A. And what is strain? Is equal to delta by L. So you can write the values here. P by A. Let's keep E as like this, delta by L, and that equal to, calculate in terms of delta, this will be equal to PL upon AE. So your deformation is PL upon AE. So what will be the strain energy? Strain energy will be, R is also, as I said, will be equal to P. So this is P times delta is PL upon AE. Multiply A from on the both sides, so this will become A square. So this is P square upon A square. P square upon A square, A L upon E. This P square upon A square can be said as stress square times AL upon E. AL upon, sorry, this will be 1 by 2 is also there, no? 2E, L upon E. Sigma square upon 2E times AL. AL is also known as volume. So you can say that this is sigma square upon 2E times volume, which is volume is AL. So this may be the expression for strain energy. This may be the expression for strain energy when we have loaded our beam like this. Sigma square 2E volume. Remember that we are obtaining strain energy in terms of different in terms of, like in this case we have obtained the strain energy in terms of load and displacement. Here the displacement is like this, so we have obtained now the strain energy U in terms of stress, only in terms of stress and the area and volume, area and length, so this becomes volume. So if in this case I only require my dimensions, and I require the modulus, the stress will be given to me, so I'll be obtaining the strain energy for me, correct? So just to tell you that this thing is also sigma square 2e upon upon 2e times volume is also known as resilience, and if you keep this U as, this is a capital U, so let's keep this as per unit volume. So per unit volume, so in the case of per unit volume, your volume, you will be dividing it by the volume, so your strain energy U becomes sigma square upon 2e, and that will be, since it's per unit volume, so this is not exactly strain energy, it is strain energy density, sigma square upon 2e. This is strain energy density. It is to be noted that the strain energy density from here can be further derived like this to half sigma epsilon. You can derive your strain energy like this also. I request you to do this by yourself. This is strain energy density. Remember that this is strain energy density. This is not strain energy per unit volume. So remember to take the volume and obtain it in terms of stress and strain. This is more important. This is more relevant to us. Either the strain energy is relevant in terms of load and displacement, or the strain energy is relevant in terms of stress and strain, because these are the two main things in most of the cases that we have. So strain energy is directly can be obtained in this fashion. Remember that this is strain energy per unit volume, also known as strain energy density. And in elasticity, it's also a science higher to solid mechanics. You will see that this is in terms of component form, this is written. That means sigma epsilon here, since you are loading it only in one direction, you will be getting sigma and epsilon in one direction. However, if you are loading in multi-axial direction, there will be certain or different components occurring in all the directions. So sigma and epsilon you have to calculate. So in that case, you will be calculating like this, and sigma 1 1 epsilon 1 1, sigma 2 2 epsilon 2 2, 3 3 epsilon 3 3, and so on with shears also. Okay, so this sigma epsilon here means sigma epsilon for uniaxial loading. So for uniaxial loading, you are applying, you will be getting the stress by P by A, obtaining the strain by strain gauge here, so you can use sigma epsilon here. But if it is a solid and if it will be having a multi-axial loading, not exactly like this, it will be having, let's say in this case, in a typical case that we have applying a load. So this is a loading condition. This is not a uniaxial loading condition. This is a multi-axial loading condition. The stress tensor will be in 3D, and it will assume, all the components will assume values, because this is not occurring usually only in one direction. If you have, let's say, one more load like this, or some moment here. So if you have such type of loading, many loads are occurring, so your stress tensor, in your stress tensor, all the components will be active. All the 6 components will be active. Remember, due to shear, I'm saying not 9, I'm saying 6. So all the 6 components will be active. So you have to obtain strain energy in summation mode, sigma epsilon plus, like this, adding up together. So in this way, this is very important expression. This is strain energy density, that is per unit volume, is very important expression. Important in the sense that it does not include material properties. Further, it does not include the dimensions of the specimen. That means you are loading, whatever the kind of loading you have, whatever the kind of loading specimen you have, it doesn't include the dimensions. Some may be using a smaller specimen, some may be using a higher specimen. So this is a very unique expression of strain energy density. And how this is obtained? This is obtained, you have to obtain it by yourself, just by rearranging these things. You will be obtaining this. Very easy to obtain. And remember that since it's a strain energy density, to volume must also come here. When you obtain it, volume must also come out. So you will be dividing by volume, per unit volume, then it becomes a strain energy. Okay. So this is the case. Okay. So now let's talk about bending. If you have any problem in this, you can write in the comment section. I will be happy to answer. This is a very straightforward basic thing. The most important thing to remember here is the strain energy density. And why this is important? As I said, this does not include any dimensions, as it is per unit volume. So it does not include any dimensions. Further, it does not include the constitutive material properties also. It does not include the modulus. So that's why this equation becomes important. It only requires the strain components, the stress components. Okay, so now let's talk about other kind of loading condition, which is also known as bending. So since this is a most of the kind of, we are going in a stepwise direction, so let me tell you something about bending. As I have given you the example that in case of a bending, your bar becomes a beam. In case of a bending, you doing the bending, your bar becomes a beam. So bending occurs on the beam, mostly on the beams. So since this is a bit larger in size, I'll take the pen. So there are different ways by which bending can be applied on the beam. So if you have a beam, and if it is fixed from this side, let's say it's fixed from this side, you apply a load on this span, then this will be called as a cantilever beam. You can apply load here, you can apply a point load here, you can apply a uniformly distributed load here. Point load in the sense that if this is some kind of a structure fixed from this side, a person is standing, so this will be approximately as a point load. Or if let's say a crate of a cold drink is placed on this beam, then this will be a uniformly distributed load. So these are different kinds of load. If such type of supports are given to you, then this is a cantilever beam. If you have been given such type of support like this, this is fixed. This means that this is fixed, like I was doing in this fashion, for that beam. fixing from this, no displacements, no rotations from this side, no displacements and no rotation from this side. Now I can bend the beam like this, I can bend the beam like this, the way I want. So this also happens in most of the railway lines, bridges. You have seen this type of beam is called as simply supported beam. There are other beams also, overhang beam and so on, but for now we are not discussing all these things. We would like to tell you the strain energy obtaining inside the when the beam is loaded. What will be the strain energy obtained? So let's take this example of a simply supported beam, and let's say a simply supported beam is placed here, and this beam is simply supported, and now this is a load span. That means any load can be applied on this. You can apply a point load, simply supported load, whatever load you are going to apply, it will experience a bending. It will experience a bending. So when the bending will occur, there will be this kind of a movement. A curvature is formed. So if you subtend a particular angle at this location, this will be a particular angle. When the beam is bended, a particular angle theta is obtained at the center. And the same thing, this arc here or this length will be called as R. So let's say we have a small element at this location. Let's bring that out and let's say zoom it, and let's say we have that element as ds. Since this is ds, this will also subtend an angle at some center above. Again this will be R and this will be theta. Remember that this theta is called as flexural rotation. Flexing means trying to bend it. Flexural. Flexing means trying to bend the beam. This is flexing. So flexural rotation. This is a flexural rotation. So this is theta. So this is SSB or simply supported beam subjected to bending, and let's say small length ds is taken, subtracting angle theta at center due to bending. So in this case your ds becomes let's try to take this triangle here. Try to take this triangle, and let's say this is ds by 2. So let's suppose, though this is a curvature, this will act like a curvature. For simplicity, let's say this is a bit linear here. This is r and this is theta by 2. So for this case, if this is my perpendicular, my ds by 2 r becomes sine theta by 2. Perpendicular upon hypotenuse, sine theta by 2, and sine theta by 2, since this is a very small element, the rotations will be very small, so we are approximately equal to d theta by 2 for small theta. So ds upon 2r equals to d theta by 2. Cancel out 2. This will give you ds will be equal to r. ds will be equal to r d theta. So this I wanted to know, what is ds? ds is equal to r d theta. Further, in the bending, there is a separate chapter of bending. When you go through that bending chapter, you will be exposed to a bending equation, very famous equation, which is derived like this only. The way I am doing it, derived like this only, and this equation is a bending equation, and that bending equation is bending equation is m upon I is equal to sigma upon y is equal to E upon R. And let me tell you some of these variables. M is a moment, applied moment. I is the inertia of the structure that you have. Sigma, applied load. Y, then you have modulus, and R you know what it is. So this is a very famous bending equation. You can go through in the books and see if people don't know what this is. This is a very famous. My aim here is not to write the bending equation. My aim here is to make you understand how to obtain the strain energy from these bending equations. So since we have this relation of ds equals to r d theta, just put it in this case. Take these two. If you put it in this will become d theta is equal to ds m upon ei, using this equation, these two terms only. Correct? D theta equals to ds m upon ei. Now look at this, very important. We have been there. All this thing has been done to obtain this. M is a moment. This is applied moment. Whatever you will apply, this will be shown here. E is a modulus, irrelevant. I is a structural, for structure. I will be different for different. I will usually depends upon the cross section of the beam. So my d theta is directly proportional to m. This is what it is. Let me show you here. My d theta is directly proportional to m, isn't it? ds is a very small, almost nothing length. Modulus is E, constant. I is also depending upon the cross section. So things that will change. What are the things that will change? Always remember that even if you will say that ds will be higher, it will change upon the applied bending moment. So this also depends upon m. So my d theta and m's are directly related. D theta and m is directly related, and they have a linear relationship between the two. As I am going to increase my moment, my theta that is subtended at the center, at the top, will become higher and higher. As you increase this, the angle will become higher and higher. So there is a linear relationship between the two, and if you make a graph of this, graph of bending moment and d theta, increasing theta, if you make a graph of this graph is linear because the relationship is linear. This graph is linear because the relationship is directly linear, and this is gradually increasing. I am increasing the bending moment gradually. Okay, so area under this curve will be work done, and that is my energy. So U equals to half m d theta, md theta, and this is equals to half m square, same thing, same expression, I can put it here, m square ds upon ei. From this I can put the expression here, in d theta expression here, m square ds upon ei. This will be my strain energy acting when there is some bending moment occurring. So my strain energy will be half m square ds upon ei. And remember that I am calculating the strain energy over this length. I have, let's say this have a length of L. So my strain energy I have obtained for ds only, for the small. So for US and for complete U, my strain energy will be half integration from 0 to L, m square ds upon 2EI, or this will be equal to m square L upon 2EI. This will be my equation for the strain energy, m square L upon 2EI. L will be the length of the beam, m will be the applied moment, and these are the material properties and moment of inertia. Again saying that moments will depend upon the cross section of the beam. So this will be this kind of a case in case of a beam that is like simply supported, which is simply supported. There may be, as I said earlier, there may be beam like this also, like a cantilever beam also. What will be the bending moment case of a cantilever beam? This will be, now in the cantilever beam also we can apply load P here, or we can apply UDL. So for different cases we will try to see. So for a case of a cantilever, so let's say a point load at free end, load at free end. So we have a cantilever and we have a beam which is having a point load P on the span L, on the span L. So my bending moment will be remember that this is a bending moment trying to rotate it in a clockwise fashion. This is fixed, trying to rotate it in a clockwise fashion. So this will be P times, let's say at any cross section X, from this to this will be X. So my bending moment will be minus Px. I am trying to obtain, remember, I am trying to obtain the strain energy. So I will try to obtain strain energy for any of this at a particular section, then I will integrate it to my overall length. So at any cross section X from a distance X, XX from distance X, my bending moment will be minus Px. Why minus? Because it is rotating my beam in clockwise. We used to take anti-clockwise movements as positive. So this becomes P times X. This is not, so this is X. So my U will be integral 0 to L. Equation was like this. So this will be minus Px square, and this is, since it is a length, so this will be dx times 2EI. This will become P square L cube upon 6EI. P square L cube upon 6EI. So what has been done in these books now? They are taking a load for different conditions and they are already telling you the expressions how to obtain them. They are taking a beam, taking a particular load, already telling you the expressions how to obtain them, and if something like this comes in the numerical, you take these equations and solve it. This is what is happening. So I would like you to do it for yourself, so that if any general equation is obtained or if any general question is given to you, you will be able to do it. And for a case of a, now the loading can be uniformly distributed. So there may be a case of UDL, uniformly distributed load. So for that case, in a case of a cantilever, let's say we have a uniformly distributed load on this, W, it's acting in per meter on a length of L. So my bending moment M will be minus Wx square by 2 at any cross section X from a distance X. Wx will be the bending moment, X by 2 in the center. Wx will be the bending moment, what will be? Wx minus, because it is trying to rotate in a clockwise, so becomes minus Wx will be the bending moment, and X by 2 because we used to take it at a center. Make this load as a point load. You have seen this in first year engineering mechanics. This is, if you have not, then please go back and just look at how the bending moments are obtained. minus sign for the clockwise rotation, since we are taking anti-clockwise as positive, wx because w times x is the span for xx, x is the span wx, and x by 2 because we used to take it UDL, we used to make UDL as a point load, so point load occurs at x by 2. This is how I hope you all know this. Then the u becomes, again put it in the same equation, and your equation will become integral 0 to L minus wx square by 2 dx upon 2 ei. So this will become w square L5 upon 40 ei. So w square, so these expressions in the book people have obtained it 40 ei. So this nothing conclusive is coming from this, as you can see. For a point load, I think you should always go back and do it for yourself. For different cases this becomes a problem to you only. This is a kind of a problem only that we are solving. This is also kind of a problem in which load is there. Now I can apply two loads simultaneously. How will you solve it? You won't be given you may be given different kinds of loading situation. So this is a point load, and also in the point load you will may be applying a UDL also being applied in that case. So remember that for a particular purely applied P, this is the case. For purely applied W, this is the case. So in these cases, these things goes on changing. Okay, these things goes on changing, but the point remains the same. There may be another case for SSB. So there may be a case of bending moment for simply supported beam that we have done earlier. Let's say the simply supported beam has a point load P at center and the length is L. So you can make bending moment in these diagrams. So bending moment, or M in your case, will be P. Let's say a distance x is there, px by 2 will be the bending moment, and the energy will be p square L cube upon 96 ei. P square L cube upon 96 ei will be the amount of strain energy obtained due to the application of this load. Remember that in this case the bending moment will be, if you make a shear force and bending moment diagram, your bending moment will be maximum at this and here. So this will be a maximum. This will be PL by 4 will be the maximum bending moment, and at any cross section XX this will be px by 2 from this distance x. And similarly you may be having bending moment for UDL. Bending moment for UDL. So I request you to obtain the bending moment for UDL by yourself, and in another video we'll be discussing the problems relating with the normal loading that we have seen and the bending, case of a bending. Seeing the case of a normal and a bending. These two things we will cover. See some 2 or 3 problems we will going to see for you. So thank you for now.